Let's continue with the geometric considerations of rolling process. I will start with an image here. You see in this first case, it's actually the common problem in the rolling. If you do not design your rolls in a different way, then that is the problem you're going to have. What is the problem? As you see, the resulting workpiece have a higher thickness at the center, at the middle, but its thickness is lower compared to center on the side of this workpiece. And this phenomenon is called as crumb, and we have a simple solution for that. If you design your rollers such that their thickness at the center is larger and their thickness is lower at the sides, then once you do the same process, then resulting workpiece will have a uniform thickness all around. And this actually happens due to the bending in the rolls, as you see here, bending on the shaft. Since we are applying too much force, applying compressive forces, this is a problem we have once you don't design your rolls accordingly. Another problem is actually spreading. Obviously, this may not be a problem since you know that once you decrease the thickness, its width will be increased. You see here, for instance, this is a side view, and if you look at the top view, obviously, after the initial width was W0, now we are in WF, which is larger than the initial width. And this happens all the time, especially if you have high thickness, initial thickness to final thickness ratios. But if the ratio is not too high, then you have less spreading. Then we have another problem, vibration and chatter. It's again is in the case of machining. There again problem in this manufacturing process, and this happens usually if you have actually tandem mills. If their let's say forces are quite high, you may have such vibration and chatter. If you remember, chatter was high frequency, low amplitude vibration. So once you have them, then you have some marks, some less quality surfaces. So this is a big problem, and we need to reduce vibration and chatter in this rolling process. How we can do it? We can increase the distance actually between the stands of the roll mills, or we can increase the width of our strip material so that we will have much more contact with the rolls. Or again, in the rolling force, actually, as in the case of rolling forces, we can decrease the amount of actually reduction per pass. If the thickness is not reducing too much, then probably you're not going to have too much vibration. Or we may increase the roll radius. We may be using larger radius so that again you have more contact length will be increased, and the vibration, the chatter problem may be eliminated. Now let's focus on the practice, the flat rolling practice. Actually, I mentioned some of the fundamentals, but let's go over them once again. So we said that the process can be done at high temperatures. If the temperature is above the recrystallization temperature of the material, then it's called as hot rolling. And we do hot rolling after the casting process. In the casting, we know that there are different types of grains, dendritic type of structures, and they are quite brittle and have porosity in between. So you don't want to have such actually striations, such grains, such larger grains. So what we do, we first do hot rolling, and with the help of it, the casted product is converted into an rolled structure, in which actually we have a bit smaller grains and their ductility, the ductility of the workpiece is a bit improved. And lastly, with the help of the forces, compressive forces, the porous regions are eliminated. We have less porosity in the rolled structures. And furthermore, we can do cold rolling, and as you know, this is done at the room temperature, and the advantage is that with the help of it, the surface quality of the material is highly increased, and we have better dimension tolerances, and we have better strength. And you can see what happens here actually. This is a road product. You see we have larger grains, and then doing a rolling process, the size of them is actually decreased. And now we have smaller grains that are forming, so we have better mechanical properties. And in this process, in this rolling process, sometimes we have problems. What are these? For instance, we have some examples here. We may have such a wavy product. This happens due to the actually bending of your rolls, or we may have some cracks, internal cracks, or cracks at the side surfaces, side regions, and these are actually due to the low ductility of the workpiece, especially at the rolling temperature. Or we may have such a weird case, it's called as agitating, and this happens due to the defects you have at the center of your workpiece, or if you have some different materials or high porosity inside your workpiece, then you may have an alligatoring effect, and this happens not all the time, but rarely, and it's mainly due to the problems in your casted material. Another thing we have in the rolling process, the residual stresses. During actually applying compressive forces, we develop some compressive forces, residual stress at the top surface, but we obviously have tensile forces, tensile stresses at the core of the material. And it is actually vice versa if you are using a larger diameter workpiece, but if you are using smaller ones, this is the case. But once the size, the diameter of the roll is increased, then we will have tensile forces at the surface, but compressive forces at the center of our workpiece. So you should be careful about it, and depending on your application, you may go with larger radius or smaller radius of rolls. And we discussed that the cold rolling process is much better, especially for the surface quality, and it's also surface softness. Its surface softness is better than hot rolling process, and these are we can say about such quality things.